Okay, so we should be recording. And press this and press this. Okay. All right, the quiz is now past due, as you know. So now that it's past due, I can go over it. And I'll probably have it for you by tomorrow sometime. Okay, integral from 1 to 8 of the cube root of x minus 1 over x dx. This is x to the 1/3 power minus 1 over x. So power root, x to the 4/3 divided by 4/3, but you know and I know if you divide by 4/3, you multiply by 3/4. And I'll let you always go straight to this. If there's a fraction involved, okay, you know and I know that if you divide by a fraction, you multiply by the reciprocal, right? So you may immediately just switch it over to like this, okay? X to the 4/3 divided by 4/3, divided by 4/3 means times 3/4, minus ln absolute value of x. Okay, plug in 8 and 8. So 3/4 times 8 to the 4/3 minus ln. Absolute value of 8 is 8. So you should leave your answer without the bars. I mentioned that to some of you. Okay. Minus plug in 1. 3/4. 1 to the 4/3 power is still 1. Minus ln, absolute value of 1. But ln of 1 is 0. So that's gone. 8 to the 4/3, you might recall that means take the cube root and the 4th power. So remember, this is power, this is root. Maybe I'll write that. This is power root. So the cube root of 8 is 2. And then 2 to the 4th power is 16. So I have 3/4 times 16 minus ln 8 minus 3/4, and we know that that's 0. Okay. And 3/4 times 16. 16 divided by 4 is 4. 3 times 4 is 12. So 12 minus natural log of 8 minus 3/4. So 12 minus 3/4 is 11 1/4, or 45 over 4. So final answer, 45 over 4 minus ln 8. If you put 11 1/4, that's okay. If you put 11.25, that's okay. Again, your final answer should not be absolute value of 8. After all, what is the absolute value of 8? It's 8. Okay, so that's for I'm willing to forgive it for this time, but I may not be so forgiving on the exam. Okay, if you have the absolute value of something and you know it's positive, then drop the bars. Okay, so that's the answer. So I'll be grading them shortly. Now, you don't have to have it completely correct in order to get full credit. I'll look at, how everybody else in your breakout group did. Or you may have missed one small thing, but everybody else was fine. I still may give you full credit. So I'll see how that goes. Okay, so that's basically it. But from here on out, everybody's responsible for their own quiz. So Thursday, I plan to give you another quiz at the end of class. So same thing, end of class. I'll put you in the breakout rooms of either 3 or 4, and you can help each other out, but everybody's responsible for their own quiz. Okay, so you don't have to worry. Well, I'm not going to say you don't have to worry about your other breakout room members. I mean, you're supposed to help them somewhat, but I'll grade the quizzes individually. But yeah, chat with each other. I think we should do this. I think we should do that. And same thing, it isn't due until the next class period, so you don't have to submit it until Tuesday, 7:10 p.m. But if you want to submit it early, that's great. You're certainly allowed to do that. Okay, so that's it for the quiz. Okay, so I'll put that away. And now, moving right along. Okay, so here we are. As it stands right now, I think I'm a little bit ahead. I was only supposed to go up to 6.2 today. I'm almost done with 6.2. In fact, I was only going to do one more problem in 6.2 and then start 6.3. Okay, so now I'm not going to stop. I'm just going to keep going. I don't know what's going to happen. My computer might die, or I might get sick, or all kinds of crazy things might happen. So if I have a chance to get ahead, I'll get ahead. Okay, but in any event, I'll try to get to the point where I can stop early and let you ask questions after a while. So I'm aiming to finish 6.2 and start sum of 6-3. Okay. Again, game plan, we're aiming for the first exam to be what, Tuesday, September the 8th for the first test. It'll be the second half of class. So the first half, I will start with lecture. So we're not going to have the whole 2 hours and 15 minutes just for the exam. Okay. Now, if I taught this class, let's say, Monday through Friday, you would get 50 minutes. So to be fair, I'm only promising you 50 minutes, but if I have a chance, I'll give you more. Okay. So whenever we have an exam, I'll start with new material. I'll start with new material. I'll stop, take questions, and then after the break, we'll take the exam. Okay. And what does it cover? Everything here. So you're responsible for all this. And please remember my 70% rule. You must submit at least 70% of the homework in order for me to grade your exam. So if you don't turn in 70% or you don't turn in any homework, then guess what? I don't grade your exam. It counts as a 0. Okay. And frankly, in my opinion, it shouldn't be that hard to get to 70%. After all, I end up doing, 30%, 40% of the problems, maybe even half the problems. Okay, so it's not that much more for you to get the full 70%. Oh, a quick word. Somebody might ask, do I have to reorder the problems? No, you don't. Okay, so you know how I jump around, right? I do 1 and then 5 and then 13 or whatever. And you say, do I have to go back and put them in order 1, 3, 5? No, you don't have to. Okay, any way that's good for you. Now, if you want to reorder them just for your own sake, you may. But if you want to just have the problems that I did and then go back on a separate sheet of paper, right? And say, okay, he didn't do problem 3 and he didn't do problem, 21 or whatever, and just attach it that way. That's perfectly fine by me. Okay. All right, and I think I sent you an announcement over Canvas. Skip problem 23 also. Okay. I apologize. This is going to happen a lot during the semester. My original homework list was from the 7th edition, and it doesn't quite match up the 8th all the time. Okay, but even if they don't match up, I'm still giving you material to learn, so to speak. Okay, and you just end up doing the rest of the problems. Okay, so that is that. So say, how do I study for the test? Here it is. Okay, and say, how many questions do I usually give on a test? I usually give about 10 questions. 10 questions, very representative of this. So let's see, if there are 1, 2, 3, 4, 5 sections, then I guess it'd be fair to have 2 questions from every section. So maybe 2 here, 2 here, 2 here, 2 here, 2 here. Now that's not an absolute promise, but that's a nice way to think of it, I guess, is the way to say it. Okay, and you already have practice taking pictures on your cell phone and submitting it to me, right? So on the exam day, you take a picture of all your homework. So, just get out your cell phone and click, 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 take a picture of all your homework, and then do the same thing for the test, right? So you have your test, you got your page or pages of your test, and just, click, 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 and just submit it to me, just like you did for the quizzes, okay? So that's how that's going to work. All right, so 6.2, let's go back to 6.2 now. And I was only going to show you one more problem, which was 15. Okay, so get the text on that. 15. I apologize. You might see my screen go yellow every now and then, and I don't know why. I'm not doing anything. So you might be saying, "What are you doing?" I'm not doing anything. It just does it on its own. So if you see a yellow screen, sorry. But then after a while, it goes away. Okay. So we have. You can't see it maybe, but it's y equals x cubed, y equals 0, x equals 1, spin it about x equals 2. Okay, so 6.2, again, maybe I'll show it to you one more time. I'll try to change the angles when you go back and look at the recording. Maybe you can find a good angle that works best for you. There's 19 through 22, I suppose, for that. And there's some more there. And there's 23 through 29. Sorry about the yellow. Okay, maybe I'll just read it. 23 says R2 about OA, R2 about OA. 25 is R2 about AB, R2 about AB. 27, R3 about OA, R3 about OA. And 29, R3 about AB, R3 about AB. Obviously, if you have the text, just look at the text. It's a lot easier than what blurry thing I'm going to give you. Okay. So here we go. Y equals x cubed, bounded by y equals 0. Y equals 0 is the same thing as the x-axis. and x equals 1. What kind of a line is x equals 1? X equals 1 is a vertical line. So this is my picture. X cubed, the x-axis, y equals 0, x equals 1, and I'm spinning it about x equals 2. So I'm taking this picture and spinning it way over here. Okay, so in order for me to do this, if I'm spinning it this way, here's my slices. My slices are with a delta y. So I'm going to integrate with respect to y, okay, in order to see the disk. Okay, so I have to solve x as a function of y. That's not too bad. How do you solve for x right here? Take the cube root. So cube root, x is equal to the cube root of y. So I take this thing and spin it way over here. Okay, and remember what we're integrating is pi r squared. So the formula for the disk method is you're integrating pi r squared, and the so-called washer is really pi big R squared minus pi little r squared. Okay, so this is my big R all the way here, and this is my little r. Okay, well, my little r is easy. It's just going to be 1. Right? So everywhere if I go up and down this line, the distance from here to here is always going to be 1. How do I know? Well, this is x equals 1. This is x equals 2. So my little radius is 1. That's what I'm throwing out. So if I take this thing and spin it way over here, okay, imagine I take this whole thing, I'm tracing it out, although you don't really have to know that here. I'm tracing this out, and I'm subtracting the trace here, you see. Okay, so the little r is 1. The question is, what's the big R? So it's the distance from here to here. And then we have to figure that out. So you say, how do I figure that out? Well, how far is it from here to here? From between my two pens? That's 2 units. Right? From here to here, anywhere here, it's 2. And how far is it from here to here, anywhere along the curve? Well, that's what we normally call x. Right? That's getting back to this fundamental picture here. If I have x comma y, this distance is x, and this distance is y. Right? So this is x. All right, so if this is 2, and this is x, can you guess what this would be? 2 minus x. So big R is 2 minus x, but what is x? X is the cube root of y. Okay, so that's my big R. That's probably the hardest part of it. Okay, so one more time. The way we integrate for the disk method, D-I-S-K, is pi r squared. The washer method, W-A-S-H-E-R, washer is really a disk minus a disk. You have a bigger radius, a smaller radius. So pi big R squared minus pi little r squared. The little r is obviously 1. As I go all the way up these slices, little r is 1. How about the bigger radius? Well, I know this is 2. The distance from any point in the curve, even as I move along, it's always x. Look at this picture. So if this is 2, and this is x, this is 2 minus x. So 2 minus x, and what's x? X is the cube root of y. And there we go. So I'm all set. So the volume is the integral from 0 to 1. We're integrating with respect to y. So pi big radius squared minus pi little radius squared. The big R is 2 minus cube root of y squared minus pi times 1 squared dy. And I just say etc. You try to do the rest of that. Okay, it's some heavy duty algebra, but this is the hardest part to set this up. Let you try the rest on your own. Obviously, I would start off by factoring out the pi. 1 squared is easy, 1 squared is 1. The maybe harder part now is to square this the right way, right? How do you square 2 minus cube root of y? So I'll let you try that on your own sometime. But other than that, I was pretty much done with 6.2. Okay, so now I'm going to start some of 6.3. So we'll see how far we get. Okay, so going into the game plan, I was supposed to only finish 6.2 today. So, but no, you don't get to leave yet. Again, I might as well get ahead if I can, because who knows, I might fall behind later. Okay, so I've already done all I needed to do according to schedule, but I'll sneak in some of 6.3 right now. It just makes it easier for us a little bit later on. Okay, so 6.3 is on something called the shell method now. Shell, S-H-E-L-L, for 6.3. Look in the book. It's on page 449. Volumes by cylindrical shells. So 6.2 is called the disk method. 6.3 is called the shell method. Okay. And you say, how do you do the shell method now? Okay. Well, start off with this picture here. You don't have to write anything. It's all theoretical. Okay. Suppose I take this region. It's y equals 2x squared minus x cubed. That's not important. This is the shape. You want to spin it about the y-axis. So they get a little piece here. Okay. So if I spin it like this, like the previous problems, we would have to solve x as a function of y. Okay. So I need x as a function of y. That's not easy to do here. Okay. For 2x squared minus x cubed, you can't really solve it for x easily, or it might even be impossible. Okay. So we can't do it that way. We have to do it another way. Okay. So we're doing something called cylindrical shells. And to motivate that, let me show you what I got here now. Okay, so the shell method. Okay, suppose I have something that looks like this. It's like a can. Can you imagine a can? Like in a supermarket? I don't know, can of corn, can of soup, or whatever. Okay. I want to try to find the volume of just the shell. Okay, not the inside. Okay, just the outside. So let's say if you have a can of corn, okay, I want the volume of just the metal, the very thin metal. Okay, no top, no bottom. Does that make sense? Okay, one more time. Suppose you have a can of corn or can of soup. Pretend there's no top, no bottom. I want the volume of just the metal, not the inside stuff, not the corn, not the soup, just the actual metal. So it's going to be very thin, right? So I'll write this. I'll write R for radius, height, and delta R. Okay, no top, no bottom. Okay, now I'm going to ask you to imagine, suppose I cut this can, no top, no bottom. If I cut it and kind of open it up so it looks like this, okay, I have a very, very thin rectangular box. It's kind of like a box, right? Imagine you take a can of corn, no top, no bottom, okay, you only have the side. If I cut it and open it up, it's a rectangle, right? And a very, very thin delta R here. And I have an H. Now, see if you can get this. If I cut and open it up, this bottom spreads all the way out. Well, that's just the circumference of the circle, is it not? Okay, if I cut and open it out, you have the circumference of the circle, 2 pi r. Now, you might say, well, the inside radius and the outside radius aren't the same, and that's true. If delta r isn't small, it's significant. Okay, but if delta r is very small, again, the calculus concept, as delta r approaches 0, the language we use in Calc 1, then the inside radius and the outside radius are practically the same. So I have this picture, 2 pi r times delta r times h. Okay, so the volume, I'll call it delta V. Again, the triangle means delta, means a little change. Delta means change. Delta V. So how do I find the volume of a box? Well, it's length times width times height. So we're going to say circumference times the height times the thickness, 2 pi r h delta r. Okay. In short, it's circumference times the height times the thickness. Okay. When we actually integrate, the delta r is going to either be delta x or delta y. It's going to be either delta x or delta y. When you integrate, it changes to dx or dy. So essentially what you're integrating is 2 pi r h. Okay, so if you want something quick and dirty to put down for integrating by the shell method, you're integrating 2 pi r h. And if you want to put that in your cheat sheet, you may. 2 pi r h is what you're integrating. Okay, circumference times height times thickness, but you don't really have to worry about the thickness. The delta r is delta y or delta x, which means when you integrate, it becomes dy or dx. So you're integrating 2 pi r h. So in short, when you're doing the previous method, disk method, you're integrating pi r squared. For the shell method, you're integrating 2 pi r h. Okay, now I'll show that to you also here. Well, this one actually comes out a little bit clearer. Page 450 in the book, just like I had. Volume is 2 pi r h delta r. Circumference times the height times the thickness. It says that's how you remember it. Okay, you don't have to remember it. I'm letting you put this on a formula sheet. Okay, by the way, this is getting off the topic, but if I were teaching you guys in a regular semester and we met on campus and there wasn't COVID and all this stuff, I would have made you memorize it. Okay, but since we're under the pandemic and everything's different, we were told, okay, loosen the standards a little bit. So my loosening of the standards is I'm going to let you have a formula sheet for exams. Okay, so maybe in one sense, it's fortunate you're taking me this semester where you get to have a formula sheet for the test, because maybe next semester, I don't know, but if next semester we're back on campus, then guess what? If I teach this class, you don't get to have a formula sheet, at least most of the time. Okay, so circumference times the height times the thickness. All right, now let's look at this theoretical picture. I have a function y equals f of x between a and b. Okay, so I've got this, this, and this. Okay, maybe I'll change the color a little bit. I'll try to make it a little bit reddish. I don't know if you can see it. Okay, now if I spin this thing about the x-axis, that's the disk method, just like before. Okay, but we're spinning it about the y-axis this time. We're going this way. Okay. So if I take this one slice, and by the way, I know I'm leaving off a lot of stuff, but if I chop this up in a whole bunch of pieces, chop, 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 chop. Okay, here's a representative chop. If I take this one thing, spin it about the y-axis, you end up with something that looks like this. It's kind of hard to visualize, but if you take this, spin it around, you basically get the outside of the can. So the formula would be circumference times height times thickness, 2 pi r h. And remember, there's more slices, okay? There's another slice here, another slice here, another slice here. I'm only drawing one slice, and the logic is let n approach infinity and let delta x approach 0, right? So that's essentially what's happening. Okay, so main difference between this method and the previous method is it looks like a picture we had before, y equals f of x between a and b. And yes, if you spin it about the x-axis, it is a disk method. But if you take this picture and spin it about the y-axis, it's the shell method. Okay, see, if I take this thing and spin it this way, you get a very thin disk. But if you take this and spin it this way, you end up with something that looks like this, whose formula is this. Okay, the other picture for this would be turn 90 degrees. If you turn it 90 degrees, you would have something that looks like this. in a similar fashion. Okay, now here's x equals a function of y. If we stop and think about it, it's kind of the same as this picture, right? So, oh yeah, there's y equals a function of x, turn it 90 degrees, okay? And that means my picture is delta y, and y goes from A to B, not x, but y goes from A to B. So if I take this picture and spin it about the y-axis, I again have a disk, okay? If I take this very small rectangular region, you might say it's not a rectangle, true, but if delta y is very, very small, for continuous functions, this graph doesn't get much of a chance to change. So if I spin it around, can you imagine I have a very, very thin disk, almost like a coin, okay? But instead, if I spin it about the x-axis, okay, I take this rectangle and spin it around the x-axis, I again have something that looks like this, only it's turned on its side. So it's another shell kind of situation. Okay, now let me show you this picture here. All right, we said we're going to integrate 2 pi RH. Okay, so what's the height? In this case, it's y. In the limit, we can just use y. Now you might say, well, the y's aren't all the same. That's true. The y value here and the y value here aren't necessarily the same. Yes, but for continuous functions, i.e. delta x approaches 0, right, then they're practically the same. And what's the radius? The distance from any point here to the y-axis is x. Again, strictly speaking, you might say, well, from here to here is not the same as here to here. It's a little bit different. It should be x1 and x2. Right, but again, if delta x is very small, in the limit, it approaches 0, then we can just call it x. Okay, so basically, in this case, you're integrating 2 pi x y because the height is y and the radius is x. Now what's happening here? This time y is the radius, x is the height. It's still going to be 2 pi xy, is it not? So that's very nice. Okay, in this circumstance, it doesn't matter if you have this picture or if you have this picture, you're still going to be basically integrating 2 pi xy. Now, I'm not going to write that down as a rule because that's only for the so-called easy case. It's a little bit harder if you have to subtract one function from another, or if you're not spinning it about the x-axis, or maybe you're spinning it about x equals 1 or y equals -2 or something like that. So I'm not going to go so far as to write down 2 pi xy. That's true here. That's true here. So yes, in the so-called easy case, it is 2 pi xy. But what's always true is 2 pi RH. Okay. So in this case, yes, it is say you're going to integrate 2 pi xy. This so-called simple case. And in this one, you also integrate 2 pi xy. But I'm going to show you some instances later where that's not the case. So I'm not so sure it's worth putting it down in general. Okay, so let's try a problem. Okay, 6.3, number 1. 6.3, number 1. Okay, if you can't see it, it's y equals x times x minus 1 squared. Let's see. Yeah. X times x minus 1 squared. Okay. And while I'm at it, let me give you more pictures here. So 454. That doesn't help. Let's switch to yellow. And here's some more. More. So some angles are a little bit better than others, I notice. So I'll just keep going around. And if you look at the video, you can just, go up or down as the case may be. And a few problems here. Let's see, how far do we have to go up to? 43. So here's 37 to 43. Okay, so maybe that's all I'll show you. All right, 6.3, number 1. They give me the picture, y equals x times x minus 1 squared, and they tell me to spin it about the y-axis. So here's a perfect example of the shell method, not the disk method. So if I take this picture and spin it about the x-axis, right, that would be a disk method. But when it's like so, that's a shell method. If you imagine taking this rectangle and spinning it, okay, you end up with something that looks like that can, that tin can that we have. So I'm integrating by formula 2 pi RH. And yes, in this so-called simplest first example, okay, the radius is x and the height is y. So yes, in this case, I am just going to integrate 2 pi xy like the previous problems. All right, so the integral is from 0 to 1, 2 pi x y. Okay, so y is the height. If you can't read that, that's ht for height. Okay, here's the circumference, 2 pi r, 2 pi x. So we're talking about circumference times height times thickness, that we were saying, right? Circumference times height times thickness. But you don't have to integrate the thickness because delta x changes to dx. So here's the circumference, here's the height. So I integrate 2 pi x times x minus 1 squared, because everything here was my original y. All right, there we go. You can factor out the 2 pi. Constants can always pass outside the integral. Okay, so 2 pi comes out. X times x is x squared. So I now have x squared times x minus 1 squared comes out to be this, x squared minus 2x plus 1. I'm sure you can all do that. 2 pi times x squared, x minus 1 squared is all this. Okay, distribute x to the 4th minus 2x cubed plus x squared, right? X squared times x squared times negative 2x, x squared times 1 is all this. Okay. All right, leave the 2 pi alone. By the way, you should always feel happy when you're integrating from 0 to 1. Those are the two easiest numbers in mathematics, right? I mean, if you have to plug in stuff, you like plugging in 0, because a lot of times when you plug in 0, you get 0. And you like plugging in 1, right? All right, so x to the 4th, x to the 5th over 5, minus 2x cubed, 2x to the 4th over 4, plus x cubed over 3. Okay. What happens when you plug in 0? Here, here, and here. You get 0. I like that, right? What happens when you plug in 1? Well, what's 1 to the 5th power? Or 1 to the 4th power? Or 1 to the 3rd power? Or 1 to anything? It's 1, right? So it's nice to have 1. So forget about this, right? 0, 0, 0. 1/5 minus 2/4 is 1/2 plus 1/3. So I just have to do this little arithmetic. 1/5 minus 1/2 plus 1/3. Common denominator is 30. So I'll multiply by 6 over 6, right? Multiply this one by 15 over 15. Multiply this one by 10 over 10. So 6 minus 15 plus 10. Okay, and that comes out to be 1, doesn't it? 6 plus 10 is 16. Minus 15 is 1. So it's 2 pi over 30. So final answer is pi over 15. All right. Okay, so what is that pi over 15? If I take this region, this funny looking thing like that, spin it about the y-axis, you get some three-dimensional shape. The volume is that. Okay. Okay, so this is called the shell method, S-H-E-L-L, shell method. For the disk method, section 2, you're basically integrating pi r squared, or maybe pi big R squared minus pi little r squared, right? That was so-called washer method. Now for the shell method, you're integrating 2 pi RH. Okay, question 5. I won't bother to show you the book. I don't want to keep bringing it back and forth, besides the book is heavy, so I don't want to do it all the time. I'll just show you what it is. Okay, so you have y equals e to the negative x squared, y equals 0, x equals 0. Those are the x and y axes, and x equals 1. Okay, so very rough sketch. And we're spinning it about the y-axis. Now you say, well, how do you know it looks like that? I just plugged in. Okay, you should know what happens when you plug in 0. You have e to the 0, which is 1. So it's up here somewhere. It doesn't have to be that exact. Then what happens if I plug in 1? I have e to the negative 1. That's like 1 over e. E is like 2.7. So 1 over 2.7, I don't know, 1/3. In any event, it goes down. Okay, so the region bounded by e to the negative x squared, y equals 0 and x equals 0, that's the x and y axes, and x equals 1. So we're taking this thing and spinning it about the y-axis, and you have y as a function of x, again. Now, if I change this to x as a function of y, I'd be doing the disk method. In this case, it's not really that convenient, because if I slice this way, well, you'd have one function here, and then all of a sudden, it just becomes x equals 1 over here. So in this case, it is easier to do your slices delta x. So we're doing the shell method. Here's my delta x. If I take this rectangular region, yes, it's not really a rectangle, but it's quote unquote almost a rectangle. Spin it about this way. I get something that looks like these shells. Okay, and once again, in this case, we have our easiest case scenario. Okay, what is the radius? The distance from here to any point on this rectangle is x. Yes, you could say x1 and x2. The distance from here to the y-axis is a little bit smaller than the distance from here to the y-axis. But again, the game we're playing is delta x approaches 0, and n, the number of slices, approaches infinity. So if that happens, you can just say it's x. And what is the height? Distance from here to here is y. So once again, we're just going to integrate 2 pi xy. All right, so here you go. You're going to go from 0 to 1, 2 pi x, y is e to the negative x squared dx. Okay, so again, 2 pi, in this case, I'm integrating 2 pi xy, 2 pi x, y was the original function, e to the negative x squared. Okay, now, the rest of the problem is a review of integration by substitution, which you had at the end of Calc 1. Okay, so I'm going to go over that one more time. Now, I don't like e to the negative x squared. I'd rather just integrate e to the u. We're going to do u substitution. Okay. Furthermore, I see the derivative of negative x squared elsewhere in the problem, except for the minus sign. Okay. So, question: what is the derivative of negative x squared? It's negative 2x. All right. Well, I see the 2. I see the x. I don't have a minus, but that's easy. I can put in the minus. I put a negative 1 inside and a negative 1 outside. Okay, so here's what we do. I do a u substitution. Sometimes we just say u sub. Let u be negative x squared. And you might say, how do you know to let u be negative x squared? Well, often the thing that's kind of complicated, that's in the way, that's what you want to simplify, right? See, I don't like e to the negative x squared. I like e to the u. So I just let this be u, and then it'll become e to the u. I know how to integrate e to the u. And furthermore, you have to have its derivative somewhere else in the problem. The derivative of negative x squared is negative 2x. I have the 2 and the x. I don't quite have a negative. That doesn't bother me. Okay, so here's how we set it up. U equals negative x squared. Du equals negative 2x dx. So you might recall from Calc 1, the way you do this, is you just change u to du, then you put the derivative, and then times dx, okay? One justification of that, you've seen this notation before, du dx. Do you remember in Calc 1, one way to write the derivative is du dx, right? So if u equals negative x squared, I could write, I don't want to, but I could put du dx equals negative 2x. So there's an over dx, right? Well, then if I multiply both sides by dx, it looks like that. And this is the way you generally would do the substitution. Okay, now what's all these funny circles thing I have here? That's where I give you the substitution. Okay, now I said the derivative of negative x squared was negative 2x, right? I have the 2, I have the x, I have the dx, I don't have the negative 1. So inside I put a negative 1, and outside I put the negative 1. So I notice I put the pi outside also. You can always take a constant inside or outside of the integral. So if I multiply by negative 1 times negative 1, what is negative 1 times negative 1? Well, it's 1. So that means I haven't changed the value of the integral. It's still going to be the same. But now, if you look at this circle right here, the next step, guess what I'm going to change negative x squared to? I'm going to change it to u, because u is equal to negative x squared. And then what's all of this weird stuff here circled? It's negative 1 times 2x times dx. You might say they're not together. It doesn't matter if they're together. Multiplication is commutative. That means you can pick this up and move it there, right? So if I pick this up and move it here, I have negative 1 times 2x dx. Negative 1 times 2x dx. I will erase all of that and change it to du. Okay, so that means instead of having this messy thing, outside I will have a pi times a negative 1. I'll have, instead of e to this mess, I'll only have e to the u. Instead of 2x dx times negative 1, I just have du, much easier integral. Now, next complication. This 0 and this 1 are for x, but I'm changing everything to u. Okay, so I need to find out if x is 0, what's the corresponding u value, and if x is 1, what's the corresponding u value. I'm going to change the whole problem so that the new problem is going to be u. So instead of x with dx, and these limits are for x, right? X goes from 0 to 1. I'm going to change it to u, du, and the limits are going to be in u also. Okay, so I asked myself, what happens when x is 0? So put a 0 right here. Negative 0 squared, that's easy, that's 0. And what happens when x is 1? Negative 1 squared, negative 1. And be careful for our order of operations. When I have negative 1 squared like that, that means you square the 1 first, which is 1, and then put on the negative. So notice my new limits of integration. The original x goes from 0 to 1. U goes from 0 to negative 1. That's the way it has to be. Okay. These limits are for x. These limits are for u. The original was x dx. I now have u du, and these numbers are for u. So I've totally forgotten about x. I'm not going to go back to x at all. I'll just do the whole problem in u, and that's it. Okay. Now, you might say, this is kind of backwards, isn't it? Usually the smaller numbers here and the bigger numbers here, right? There's a very easy remedy for that in this particular case, especially since a negative. Do you recall, maybe toward the end of Calc 1, you're allowed to switch these two and change the sign. And that's the best of both worlds. I get to change this to a positive, right? Change the sign and switch it. And now look at, this is the way I want it. Smaller number here, bigger number here, and a positive pi, right? So one more time, at the end of Calc 1, if you had the integral from a to b, you were allowed to switch these two. Switch it to the integral from b to a and change the sign. And since this was a negative already, that's perfect. Change that to a positive and say, I'm going to go from negative 1 to 0. Now, this is positive, and negative 1 is a smaller number, and 0 is the bigger number. Is that right? So it's perfect. It's exactly the way that I want it. Okay, so we're almost home free. So when I integrate, leave the pi alone. What's the integral of e to the u? It's the same thing, e to the u from -1 to 0. Okay, so pi, you can factor out the pi. So pi parentheses, plug in 0, I get e to the 0, which is 1. Plug in -1, you have e to the -1. You can just leave it. Leave it like that. So pi parentheses 1 minus e to the 1. And by the way, one exception where it's okay to leave your answer with a negative exponent is when you have e. Okay, so in other words, you don't have to go 1 over e. Okay, so you know how we say, oh, usually don't leave a negative exponent? It's okay with e. So e to the -1 turns out to be okay. Right? All right, I'll have one where we're spinning it about the x-axis, and then after that, maybe we'll take a break. Okay, the function is xy equals 1, bounded by x equals 0, y equals 1, and y equals 3. And it's said to spin it about the x-axis. Okay, xy equals 1. Okay, if I'm going to spin it this way and do the so-called disk method, my slice is going to be with delta y. So if I'm doing delta y, I need to solve x as a function of y. So how do I solve for x here? That's easy, just divide both sides by y. So x equals 1 over y. It's the same as y equals 1 over x, which looks like this. So we know this is the graph. We're going from y equals 1 to y equals 3. Those are horizontal lines. So you might recall y equals a constant, like y equals 2, y equals 80. Those are horizontal lines. If it says x equals a constant, those are vertical lines. Okay, so here's what I'm taking. This thing right here, and I'm spinning it about the x-axis in order to do the shell method. So x equals 1 over y. Okay, here's my radius. Distance from here to here is my radius. That's y. That's just y. And then the distance from here to here, that's what you normally call x. Okay. Yes, you might say, well, all the x's are not the same. Yes, but if delta y is very small for a continuous function, there's not much of a difference between this one and this one. The language we would say is as delta y approaches 0, then it doesn't matter what you pick. So this is x, this is y. So once again, in this case, we're going to integrate 2 pi xy. Yeah, I know you might say, it sure looks like a lot of problems we're just integrating 2 pi xy, but that's not always going to be the case a little bit later on. Okay, so I'm going to integrate with respect to y. If I'm integrating with respect to y, can you see what the limits of integration would be? They gave it to us. I'm going to integrate from 1 to 3. So integral from 1 to 3. Okay, so yes, I am doing circumference times height times thickness, 2 pi rh, but the r is y, and the height is x. So I'm just integrating 2 pi xy again. So 2 pi y times x. Here's x. This thing right here is x, which is 1 over y. So I'm integrating 2 pi y, 1 over y. Well, very conveniently, the y's just drop out. So I'm just integrating 2 pi, or you can factor out the 2 pi. I'm integrating 1 dy. Okay. So what's the integral of 1? Well, with respect to y, it would be y. If you say the integral of 1 is x, that's true because most of the time we integrate with dx. But here we're integrating dy. So the integral of 1 dy would be y. Right, so 2 pi y from 1 to 3. Okay, factor out the 2 pi. Just leave the 2 pi out of it. When you get a 2 pi like that, just forget about it. Plug in 3. minus plug in 1. 3 minus 1 is 2. 2 times 2 pi is 4 pi. Right? So my answer is 4 pi. Okay. All right, that'll do it for now. So I think it's a good time to break. So I'll stop sharing. I'll pause the video, and then I'll pick up from there. So let's see. How about let's start up again at 8:15? All right, roughly 8:15. So stop share, and I'll pause. Okay, so I think we're recording. And go back to share the screen. Goes through its little cycle. There's me and there's this again. Okay. All right, so I've snuck in some of 6.3. So I'm ahead of the game. So I can do a little bit of more 6.3 and then I'll stop. And then I'll let you ask questions if you have any. And then if we end early, then so be it. We end early. Okay. All right, so let me get back to where we were over here. So ignore the days. For the disk method, essentially you're integrating pi r squared. If you want to put that on your cheat sheet, you may. Right? We integrate pi r squared. That was only if you have a disk. Remember, if you have a washer, you've got a bigger region and a smaller region. You're subtracting, right? Pi big R squared minus pi little r squared. I know what. Why don't I just write that down for you here? Okay, something called the washer method. It's really the same thing, but you have two functions to consider. So you integrate pi big R squared minus pi little r squared. So it's not really a new formula. You've got an outside function and an inside function. So if you have a so-called washer method, okay, there's going to be a hole in the middle. You integrate pi big R squared minus pi little r squared. You're allowed to put that in your cheat sheet if you wish. But again, you're limited to just one of these 8.5 by 11 sheets of paper, both sides. So you budget your paper, I suppose. Okay, so that was section 2. And now section 3, the shell method, you're integrating 2 pi rh in general, where this is the circumference, 2 pi r is the formula for the circumference, and h is the height. And there is a thickness, but you don't have to worry about it. The thickness is usually either delta x or delta y. When you integrate, it becomes dx or dy, so it's not part of the function that you're integrating. Okay. All right. So let me show you 6.3, number 11. Again, I won't show you the book because I've got it right here. So the graph of y equals x cubed. Okay, quick timeout. Do you remember what the graph of y equals x cubed looks like? It's kind of like x squared in the first quadrant, but unlike y equals x squared, it goes into the third quadrant, right? So it drops down over here, but we're not using that part because it says we're bounded by x equals 0. X equals 0 is the same thing as the y-axis, and the line y equals 8. So we have this picture right here. Okay. Now, if you imagine this picture, if we spin it about the y-axis, that would be the disk method. If I take this slice right here, spin it about, okay, I would get a bowl, right? Can you visualize that bowl if I spin it around? You get a bowl.
Excuse me, Professor?
Yes.
You said number 11?
Number 11, yes.
In my book, I have y equals x to the 3/2.
Y equals x to the 3/2. You're absolutely right. So this is a different version. So let me see what's the equivalent, if there is any. As I said, sometimes it's not going to match. Maybe 15? No, it's not quite the same as 15. Or is it?
Yeah, it looks like 15.
Sort of like 15, except
Yeah.
it says to spin it about x equals 3. Okay, so I'm going to have to star this. Sorry, you guys.
Okay.
So it's 11 star, meaning I'm going to go ahead and show you the problem since I already did it, but it doesn't match with what's in our text. Okay, and that'll happen sometimes. Sorry about that. And yeah, feel free to interrupt me like that. I know I said, you know, I'm not taking any questions, but if I'm doing something really dumb and, you know, I'm doing the wrong problem, sure, feel free to interrupt me. I won't get mad at you. Okay, so if I spin this around like this, you get a bowl, but I'm going to spin it like this. So if I go this way, that's where it looks like I'm not doing this method, but the shell method. Okay, so this 11 star, which is not really one of the assigned problems. So if I go like this, the radius is y. Distance from any point to the x-axis is y. And my height here is x. Okay, well, what is x? X is equal to the cube root of y. They started off with y equals x cubed. So if I take the cube root of both sides, it looks like this. X equals cube root of y. So there we go. So if I'm integrating with respect to y, y goes from 0 to 8. So I'm going to go integral from 0 to 8 of 2 pi x y. 2 pi, I leave y alone because it's dy. And then this is x. This thing right here is like x. They didn't give it to me that way, but I had to change it. All right, so 2 pi y times the cube root of y. So now this is what I'm trying to integrate. Okay, take out the 2 pi. This is y to the 1. This is y to the 1/3. So 1 plus 1/3 is 4/3. So I'm integrating 2 pi, integral from 0 to 8, of y to the 4/3 dy. Okay, so power rule. Add 1 and divide by the new exponent. What is 1 more than 4/3? 7/3. 4/3 plus 3/3 is 7/3 divided by 7/3. And from now on, I'll just do the shortcut. If I divide by 7/3, I multiply it by 3 over 7. Okay, so this stuff right here comes out to be 6 pi over 7. Okay. Plug in 8. Plug in 0. Well, 0 to the 7/3 is 0. We like plugging in 0, right? Okay, how do you do this? What does the 3 represent? 3 represents the cube root. What is the cube root of 8? 2. And then I raise it to the 7th power. 2 to the 7th, 2 times 2 times 2 times 2 times 2 times 2 times 2. You can punch in your calculator. It's 128. Okay, multiply all this junk out. Final answer, 768 pi over 7. And again, if you have a pi, just leave the pi like that. Okay. All right, I was going to show you one more, but again, this is from the 7th edition, and I'm not sure if that problem shows up anywhere. So let's see. Y equals x to the 4th, y equals 0. So do I see anything like that in the new edition, or maybe they threw it out, unfortunately. Unfortunately, I don't see anything like it. Okay, so I'm just showing it to you anyway because I already did it, and it's good practice anyway. So I'll have to put 15 star. Again, sorry about that. That means it's not really in the book.
Could it be possible? Could it be similar to number 15 on the book?
Is it similar to 15 from the book? Kind of, but the numbers are not quite the same. The book has x cubed, and the one that I had from the 7th was x to the 4th. And so I don't see anything that's exactly like it. So, oh well, be that as it may. Okay, so let's just go with it, I guess. All right, so here's our first instance of spinning it about something else. Okay, y equals x to the 4th. Do you remember what that looks like? It opens up kind of like a parabola. We don't call it a parabola, but it's sort of like it. What is y equals 0? That's the x-axis. Right? And what is x equals 1? Vertical line. And this time I'm spinning it about the x equals 2. So here's our first instance of spinning it about a different axis than the x or y axis. Okay, so here's y equals x to the 4th. There's a piece over here, but we don't care about it right now. Y equals 0 is the x-axis. X equals 0 is the y-axis. And they want me to spin it way over here. So I did my little slices. Here's my slice with a delta x. If I spin it way over here, it's a shell, right? If I spin it this way, it's a disc. But imagine take that rectangle and bring it way around here. You end up with that can sort of thing. Okay, so what's the height? The height is y, right? From any point down to the x-axis is y. And this is my radius from here to here. So how do I get my radius? The distance from here to here is 2. Distance from here to here is x, right? So any given point here, back to the y-axis, that's x. So this is 2, this is x, this is the difference between the two, which is 2 minus x. That's my radius. So that's the key problem. That's the key part for this one. Okay. So 2 pi RH is what I integrate. 2 pi RH. So in this particular case, it's not just going to be 2 pi xy like a lot of the previous ones. 2 pi r, we argued that the r was 2 minus x. The height is y, but what is y? X to the 4th. So here we are, 2 pi RH. 2 pi, 2 minus x, x to the 4th dx. And there we go. Okay, so now just finish the integration. Take out the 2 pi. Distribute. 2 times x to the 4th. Negative x times x to the 4th. X to the 5th. And again, yes, we like going from 0 to 1. You can't beat that, right? Can't beat going from 0 to 1. So we integrate 2 pi, 2 x to the 5th over 5, power root. Leave the 2 alone. X to the 5th over 5 minus x to the 6th over 6. Plug in 0, you know you get 0, right? So 0 minus 0. Put a 0 there, that's all 0. Put a 0 there, that's all 0. Okay, plug in 1, I get 2/5 minus 1/6. Sorry if you can't read that. That's 2/5 minus 1/6. There's a 2 pi out in front. Common denominator is 30. So multiply by 6/6. 2 times 6 is 12. That's a 12 there. Multiply this by 5/5. 12 minus 5 is 7. So I have 2 pi times 7/30. 2 pi times 7/30. That 30 will cancel with a 2. Final answer is 7 pi over 15 in this particular case. Okay, and that was as much as I was going to show you for tonight. Okay, and what time is it? 8:30 something? Okay, so the rest of the time will be question and answers. I'm going to stop share. I'll stop the recording.